This is the paper. This is not an hard one. General practical principles, right? So can you all see the screen? Right. Define the isotopic mass. Yeah. Can one of you tell me what is the definition of isotopic mass? Yeah. Relative isotopic mass. Yeah. Yeah. Relative isotopic mass of an isotope, not just an atom. Mass of an isotope. Mass of an isotope relative to the mass of carbon 612 isotope. Right? Relative isotopic mass. They are not asking about relative atomic mass. Okay, what is the definition of um, or sometimes you can define it as an atom as also, but the best answer is what? Isotope, right? Every atom is an I mean, there can be some may argue if that atom is not an isotope, then how would you define it, right? Okay. Or if an element does not have an isotope, or, or likewise. So, anyways, even writing as an atom may also be included, but I would prefer writing as an isotope, right? Mass of an atom. A sample of hydrogen gas is formed from atom of three isotopes. Deduce the number of peaks due to molecular ions in the mass spectrum of the sample. These are the isotopes. Deduce the number of peaks due to the molecular. They are asking about the number of ions. You have to deduce it. How many number of atoms are there? Yeah, there are five altogether. For example, now there are two, no? So we have to look at the combinations, right? One is this one, other is this combination. Also, you can have 3, 3. Then you can swap it, right? This combination 2, 1. 2, 1 combination can be there. 2, 3 combination can be there. Uh, right. What about 3, 1 combination? What about this? How many would come then? 1, 2, 3, 4, 5. Yeah, how many are there then? How did you get 5? You say 2 plus ions. Okay, no, now they ask about type of combination. So what is your answer? What is the answer you got here for this one? Oh, she just left. Right. So altogether there are one, 2, 3, 4, 5, and 6 isotopes are there. Shall we move on to the next one? Right. Yes, so for this question, how many isotopes did you get? Yeah. How many isotopes? You got How many you got? You got five. Okay. What about six ones? You can have six combinations, right? Why not? There are no six ones. Why you can't have six? Yes. Any reason for that? Yeah. Why it is five exactly? Now they are asking about us to deduce. How did you deduce it? Yeah. Why not six? The reason is it's a very good question, right? When you talk about the masses, right? This one is having also same mass. Can you see? Three and one. They are going to have the same mass as what? Second isotope, right? So this combination and this combination is going to have the same mass. So that is the reason why you are getting only five peaks. Is it understood? Right? You are going to have six different uh, molecular ions, six different molecular ions, but they have only five different molecular ionic masses. Right? So therefore, you are going to expect only to have only five different peaks. Is it understood? I hope it is okay, right? Okay. Let's move on to next one. This question is about the intermolecular forces in organic compound. The structure of four isomeric alkanes are shown. Only significant molecular forces between molecules of these compounds are London forces. Explain how London forces arise. Yeah. Mhm. Yes, it is occurring due to the sudden differences, right? Sudden fluctuations in electron cloud of any covalent bond, right? Of any covalent bond between two atoms, right? Because of these fluctuations, a temporal polarity is formed between the two atoms, right? Temporal polarity is formed between two atoms. And this makes the molecule, this gives the molecule a temporal polarity, right? Molecules, molecule become temporary, temporarily polar, right? Temporarily polar. Right? So London forces are what? These are intermolecular forces, right? Molecular forces. Okay. And you can find them between any molecule, right? Whether it is a polar molecule or non-polar molecule, this can be there. And also, London forces are there even in what? Noble gases, right? Even in noble gases. So even if you take, it shouldn't be a molecule, even single atoms, atomic gases, like noble gases, they also can have a temporal fluctuations of the electron density due to many reasons. Maybe due to uh, presence of a electric field nearby, right? Due to presence of a ion nearby, right? It shouldn't only be due to a it should not only between a two atoms having a covalent bond, even in noble gases having only one atom also, they also can have weak London dispersion forces, right? London forces. Is it clear? Even single atoms also, uh, even single uh, atoms, you can have London dispersion forces. Right? Okay, so you are getting marks for movement of electrons and for saying instantaneous, right? Sudden fluctuations of electron densities, right? Uh, and also you can tell this is also inducing a London forces are also inducing a, it induces a dipole in an adjacent neighboring molecule, right? Inducing a dipole in the adjacent molecule, right? That can also be mentioned, right? So those are the 3 points mentioning about electron cloud, sudden changes of the electron densities, and it is inducing the polarity in the neighboring molecule, right? So yeah. Next point, explain which of the compound AD will have the highest boiling temperature. Highest boiling temperature means what? Highest boiling point. Highest boiling point is due to what? Now, highest boiling point is due to having highest intermolecular, strongest intermolecular forces, right? Strongest intermolecular interactions. So when you look at these compounds A, B, C, and D, they all are what? Uh, you can consider them as non-polar. Why? They are hydrocarbons, right? They have no polarities. But even though they are non-polar compounds, they have what? London forces between them, right? So we have to determine which one of these are having the strongest London forces, right? So we can start off with branching, right? If it is branch less, so if you compare A, B, C, D, these four, between these four, A is the least branch. Least branch means more area is what? Exposed to have, more surface area is exposed to have, or you can say more contact area is there, right? More contact area is exposed. So therefore it can have, the more area is exposed to have London dispersion forces. So therefore, since more area is exposed, stronger London forces are there in the least branched one. So their question is, so stronger London forces means greater boiling point and melting point. So what they're asking. From A to do have the highest boiling temperature. It's clear which compounds. Uh, which of the compounds? Right. So highest boiling point is for what? What is the answer? Then? A, right? A has stronger London dispersion forces because it is the least branch. So therefore more area is exposed, more surface area is exposed. Okay. So you are getting 3 points, 2 points. First point is for what? Least branch. So therefore more surface area is or more uh, point of contact, right? or they can have better packing, right? When it is branchless, can have better packing. They can get close to each other, right? Okay. Uh, let's move on to the next one. Explain which of the okay we have done that. Apparatus shown may be used in an experiment to compare how far, if at all, a charge rod deflects different liquids. And that is a very, very easy one, right? A stream of liquid is there, a beaker is there, a charge rod. So it is getting attracted towards the charge rod. So therefore it means what? You can say the polarity. A stream of liquid is attracted to the charge rod mean it must have what? A negative polarity. Uh, the structures of three compounds are shown. Explain whether or not each of these liquids will be deflected in this experiment. What is your answer? So between these, so to get deflected, so as you can see here, it is getting attracted to the positive charge. So you can assume between these three, what is the polar structure? So when you compare CH, CCl4, CHCl3, C6H14, right? Uh, between these three, this one is the one is who is having a dipole moment, right? Why? Now, when you look at here the bonds are polar, but when you look at the geometry of the molecule, right? All these polarities are getting cancelled off. Even though the bonds are polar, if you look at the overall structure, because of this tetrahedral arrangement, right? There's no dipole moment. So therefore, you can omit this compound. And here, when you consider this one also, right? It's an hydrocarbon. So so between this carbon, this bond is non-polar. Polarity is very less, and also this has a tetrahedral geometry. Hydrocarbon. So usually hydrocarbons are non-polar, or even though there's a polarity, the polarity is very low. So it's a non-polar compound. This is hydrocarbons, right? Because of the bonds between carbon is non-polar, and also when you talk about the geometry around each carbon, it is tetrahedral. So therefore, most of the time these polarities are getting cancelled off. So it's a non-polar, no zero dipole moment, or least polarity is there. But here, when you look at this molecule, this bond is polar, this bond is polar, but here between carbon and hydrogen, the polarities, electronegativities are different between carbon and hydrogen. So therefore, this bond is polar. So therefore, this molecule has a dipole moment. It's a polar molecule. So therefore, the stream must contain a polar molecule. So between these three, which is the polar one? CHCl3. Right? So how do you write the answer? Okay. Okay. Uh, so which one is the answer? CHCl3 is the answer, right? Okay. So in your 3 points, you must mention about um, bond polarities, right? When you talk about the bond polarities, CHCl3 and CCl4, both are having bond polarities. We should take a bond atom between the bond. This bond is polar, right? So this contains polar bonds. But C6H14, it is non-polar. No bond polarities, right? And the second point, the symmetry. Cl4 is a symmetric molecule, therefore, even though bonds are polar, the polarities are getting cancelled off. But when you talk about CHCl3, there's a polarity between carbon and hydrogen, and also when you talk about Cl, CCl, and CCl, these are also polar, but these polarities are stronger between these carbon and chlorine. So therefore, you can consider it as a non-symmetrical molecule because these bonds are not similar, right? So therefore, it contains a dipole moment. Uh, you cannot specify it on a specific molecular shape for hydrocarbon because it's a longer chain, but you can tell around each carbon approximately it has a uh, tetrahedral geometry, right? Okay, is it understood? Clear? A student carries out an experiment to identify group 1 metal ion in a sulfate M2SO4, right? A 0.48 gram sample of M2SO4 was added to about 50 cubic centimeters of deionized water in a beaker. The mixture was stirred with a glass rod until the sample discovered completely, right? Okay, stirred with a glass rod until the sample dissolved completely. An excess of acidified barium chloride solution was added very slowly to the solution from step 1 to ensure the crystals of barium sulfate that formed were as large as possible. Right? Let's draw a diagram. We have a sample of deionized water in a beaker. Right? You have the beaker. Beaker contains deionized water, 50 cubic centimeters. You are adding a sample of 0.48 grams M2SO4, right? A solid, and it is getting dissolved completely. Excess of barium chloride, right? The barium chloride you are adding, what happens then? It gives a precipitate. Uh, the precipitate is what? The solid is barium sulfate. It's like bread and butter questions, right? The moment they talk about a precipitate, white color precipitate with the addition of barium 2 plus ion and a sulfate 2 minus ion, it is about barium sulfate, right? Uh, and the barium sulfate crystals were collected by gravity filtration onto a dry filter paper of a known mass, and they are collecting it on a this gravity filtration, right? And on a what? Dry filter paper, they are collecting barium sulfate, right? The crystals were rinsed using deionized water, so they had to clean the remaining water, or maybe the crystals were rinsed using deionized water, right? Okay. Filter paper containing the crystals were dried and in a warm oven for an hour and then weighed. Right. So basically, what they are doing is they are measuring the weight of um, the precipitate. Right. First, they wash it with deionized water to remove any impurities in the precipitate form, and then they are drying it in an oven and weigh the mass of barium sulfate they have obtained. Right. Mass of dry filter paper is given. Mass of dry filter paper of barium sulfate crystals is also given. Give a reason with reference to the filtration in step 3 why the formation of extremely small crystals in step 2 would lead to a lower mass of dry barium sulfate. Step 3. Uh, yeah. Now what they're asking is with the reference to the filtration in step 3 why the formation of extremely low crystals. Now when you have extremely low crystals will lead to a, then why the larger if the crystals are larger, so as they say if the crystals are larger it will not lower the dry mass of barium sulfate collected at step 5, but if the crystals are smaller it is going to affect the final mass. Why when the crystals are smaller the final mass is greater, when the crystals are larger the final mass is the real mass or the correct mass. uh, why why when the crystals are smaller lower mass, when the crystals are large it means higher mass, right? What should be the reason? Yeah, tell me. During the filtration, so we are collecting from the gravity filtration, right? Gravity filtration means we are sending it to these filter papers, they have small pores, so through the pores we are sending the solution. If the crystals are so small what will happen? Yeah, what will happen if the crystals are very small, what will happen? Yes, what will happen then? It will go through the pores of the filter paper, right? If the crystals are very small it will sneak through, so the weight remaining on the filter paper will be much less, right? But if you have a bit larger crystals then it will retain here, so therefore you will get a greater mass because the percentage of crystals leaking through the small pores of the filter paper will be quite less. Okay, so you must write that point. If the crystals are very small it will go through the smaller pores of the filter paper. Explain why the crystals are rinsed in step 5, step 4. Why they are rinsed? What do you think? B part B. So for the part B, we wash it to remove excess barium chloride or MCl aqueous, right? Otherwise, you could have with the solid you could have excess barium chloride aqueous. So if you weigh the precipitate with the barium chloride aqueous, in the solid retained, then you will get a rate of mass, right? So it's better to wash it with deionized water so you can get rid of this barium chloride ions, so you can get a more accurate weight. Otherwise, it would add to the final mass at step 5. Okay, calculate from the relative formula mass of M2 sulfate and hence identify M. Calculate the relative formula mass of M2 sulfate and hence identify M. Um, MR is given. Mm, okay, MR of barium sulfate is also given. Um, so you are given the, if we go back to the experiment, mm, okay, the initial mass is given here. Right. Okay. So we can find the number of moles of M here. 0.48 divided by, let's say M is unknown, 2 M's. Sulfur is what? 32. Oxygen is 16 into 4, 64. Right? This is the number of, and this into, yeah. Uh, and this multiplied by 2 is equal to number of moles of M. Right? So this is getting precipitated. Uh, right. Then you are getting barium sulfate crystals. So this is the number of moles of M. So when you compare M and barium sulfate, right? Let's look at the ratio. So if we have one with 2 moles of M, you can precipitate 1 M of barium sulfate. With 2, you can precipitate 1 mole of barium sulfate. So it means ratio is 2 to 1. So it means half of this means this, right? So this is exactly number of moles of barium sulfate. So 0.48 divided by 2M. Here you are getting it as 96, right? Okay. Uh, and this is the number of moles of barium sulfate, right? The number of moles of barium sulfate multiplied by relative atomic mass of barium sulfate. Relative atomic mass of barium sulfate is 233.4, right? is equal to the precipitate you have obtained. The precipitate you have obtained is 0.19 minus 0.17. Okay. So you just have to make m the subject, right? Uh, so once you get the m value, based on the value of m, the value of m means relative atomic mass of m, and by looking at the periodic table, you can decide on the name of the element, right? What is the answer for m you got? Yeah. What is the m? Yeah. What did you get as the answer for m? Lithium. You are getting something around 109.85, right? 84, right? For when you look at the relative atomic mass of lithium is around 110 grams per moles, right? It's a very easy calculation, right? Another student carrying out the experiment placed the glass rod on the laboratory bench when the stirring was completed on step 1. Explain what effect this would have on the calculated value of the relative formula mass of M2SO4. Another student carrying out an experiment placed the glass rod on the laboratory bench, right? When stirring was complete in step 1 on the laboratory bench. Ah, okay. So when he or when she's stirring, what happens? She has uh, kept the rod on the table. So with the rod, she could have taken some ions away, right? That would have what precipitated with it, right? So it means you are going to get a low mass here, right? Low mass means, right? You are going to have what? If you are obtaining a low mass, explain the effect that would have been on a calculated value relative to atomic mass, right? So, so here you have m value, no? Here you have the weight, right? If you have a low mass, it means you will get a large m sulfate value, right? So you will get a greater m value, right? You are going to have in the calculation you are going to get a greater m2 sulfate value, right? While w divided by m, yes, is equal to the number of mass you obtain in the precipitate, right? So since you have obtained at least a low amount of mass, so therefore it means the value over here must be the calculation you are going to get a greater value, right? So in your calculation you are going to get a greater into SO4 value. Is it understood? Is it clear? So you just yeah, look at the formula and check, right? When the denominator value must go up if this answer is going to get a smaller value, little value, right? Okay. As another student carrying out the experiment placed the glass rod on the, okay, we discussed that. Good. Describe how the student should amend the procedure. So it means there's an issue with the procedure, right? Uh, how should the procedure be amended? Yeah. So what we can tell here is what? You can stir it with a rod, right? So I have to mention it. And then in between here, between these spaces, the rod again can be washed with deionized water, right? The washed away water must be included or collected or be with the total volume of the ions dissolved in the container, right? You must dissolve it in the deionized water, and that wash away deionized water must be included in the final volume of the sample that we are using to dissolve the salt, right? Is it clear? Right, rinse it into the beaker, right? Then there won't be any issue. Rinse it into the beaker. The other way to identify the metal ion is a flame test. Explain what causes the flame color in such a test. Ah, what is your answer in a flame test? Okay, so we are seeing color. Is it due to the excitation or de-excitation? Is it happening due to the excitation or de-excitation? Okay. Hmm. Right. So we are seeing a color, as you said, the electrons are getting excited or getting promoted into outer shells when we heat it with the flame, and again they are getting de-excited, releasing energy as radiation. So that radiation sometimes has a color, or that radiation is within the range of the visible spectrum of human, or visible spectrum of spectrum. Or sometimes this emitted radiation is within the range of visible spectrum. So therefore, we can see a color, right? Yes, when the electrons are getting promoted to excited, absorbing the energy of the flame, and again they are falling back. Uh, they are releasing energy as radiation. If the radiating energy is within the range of visible spectrum, we are starting to see a color, right? So you can write this answer in two, three lines. Okay. Give one advantage and one disadvantage using the flame test to identify a metal cation. Give one advantage or one disadvantage of using flame test to identify a metal cation rather than method followed by the student in set 1 to 5. What is the advantage of flame test? Yeah. What is the advantage? Easy and reliable. Disadvantage? Colored could some there are some metal ions they have the same color, they are within same color spectrum. There can be overlaps. Some metal ions are having the same color, or they have some, or they are within the same range actually. So therefore, to pinpoint and tell whether this is this iron or not from the naked eye, it is kind of hard. So therefore, to determine that, you will have to have a absorption spectrum. You will have to use a machine, right? You will have to have something like a colorimeter. By using a colorimeter, then using that absorbance value, you can determine what the element is. But from the naked eye, if the two metals are forming the same color, then you can't exactly tell which one of this is. There can be some overlaps in the colors, right? Same color object, uh, same color elements having the same color are there, right? Okay, right. Then I'll send the class one. This is a very good paper, and we'll continue from here next day. Okay, take care. Bye bye. Nice day. Bye bye.